Previously, we were defining pressure in terms of force. And in doing that, we gave the example of the weight of a person applied over a certain area. When we deal with pressures in the oil and gas industry and in natural gas processing, we're dealing with pressures caused by forces that are exerted by gases. So we need to take a look at how that works. It's a little different from force exerted by the weight of a body. One of the ways to visualize pressure, I think most of us are familiar with scuba tanks. Even if you haven't actually been scuba diving, you kind of understand the concept. Scuba tanks. This is a scuba tank, okay? And of course, these are used by people who go scuba diving to carry air with them under the water so that they can breathe air underwater. So one of the key things here is to put air into here and have air available to breathe while you're swimming underwater. These vessels, these scuba tanks, are designed to hold pressure. And when you add air into them, it increases the pressure in the tank. Now, why does that happen? Your book discusses pressure on page 4. They start discussing how pressure results from the movement of molecules. And when you look at pressure that is caused by gases, turns out that the pressure results from the collisions of molecules. And what you can picture is, inside a scuba tank, you would have a whole bunch of molecules of air. Now this is just like the air that's in the room that we're breathing, where all of us are sitting right now. We're all sitting somewhere, we're breathing air. Even though we can't see it, there are billions of molecules of air in the room or outside. Wherever you're sitting right now, you're surrounded by billions of molecules of air. In the case of air, it is a gas, but it's not the same gas as natural gas, obviously. Air is made up of oxygen and nitrogen and some carbon dioxide, some other things. But just like the oil field gases, the air is made up of billions and billions of tiny molecules of gas. It's not just space. There's actually a chemical there. It's tiny molecules of different elements. Now it turns out that these little molecules of gases, whether you're talking about air or the gases in the oil field, they have movement. They're all moving around kind of randomly, just random directions, and they wind up colliding with each other, and they also collide with the walls of the container. It's the collisions with the walls of the container that create the pressure, because that's actually force. Even though they're tiny, tiny molecules, there's enough of them that they apply enough force, just like the person standing on the ground. They apply force to the walls of the container, and that's where the pressure comes from. Now, the difference between a person standing on the floor or standing on your foot, the difference between that kind of pressure and the pressure exerted by gas, pressure exerted by a gas is equal in all directions. Like if you picture, if you take a balloon, you fill it up with air, or you put a little bit of air in it, like this one doesn't have a lot of air in it. It's round because the air inside of it is exerting equal pressure in all directions. Every inside surface of that balloon has an equal amount of pressure on it. Okay, when you look at the pressure related to numbers of collisions, if you increase the number of collisions of molecules, you're going to increase the pressure. These arrows mean increase. So if you increase the number of collisions, you increase the pressure. how do you increase the number of collisions? There's two main ways. One is if you increase the number of molecules. If you put more molecules in here, they're going to be more crowded. So they're going to be bumping into each other more. So you're going to have more collisions, which is going to increase pressure. The other way is if you increase the speed of the movement of the molecules. Increase their speed, they move around faster, they're going to be bumping into each other more, you're going to get higher pressure. How do you increase their speed? By increasing the temperature. So, the two main ways that you would increase pressure in a vessel like this is to increase the number of molecules or to increase the temperature by adding heat. And of course, if you do the opposite, if you decrease the number of molecules or decrease the temperature, you're going to decrease the pressure. And I think we're all familiar with, if you've ever been scuba diving, I know you know this, there's a pressure gauge on your tank that tells you how much pressure you have. And you keep an eye on that when you're scuba diving, because if you run out of air, you're in trouble. The pressure tells you how much air you have left. When you get down to a certain pressure, it's time to end your dive. And the pressure depends on two things: how many molecules there are, how many molecules of air, and also the temperature. So at the end of a dive, you may have lower pressure. You go to the dive shop, and that's because you have lower pressure because you breathed the air out of it. You took air out of it. Before you dive, you go get your scuba tank filled up. You go to a dive shop, they add air back in. When they add air back in, the pressure goes up. So you increase your pressure, and your pressure gauge will show that you have more air. So you're actually putting more molecules in there, which is increasing the pressure. Now on page 4 of your book, they talk about the ideal gas law. And that's actually a mathematical way to describe what we've been talking about. You need to be familiar with this term, ideal gas law, and you need to learn this equation, know what the letters mean, and understand the relationships. And basically it's what we've just been talking about. It's the relationships between pressure, volume, number of molecules, and temperature. So pressure, P stands for pressure, V stands for volume, N is number of molecules, T stands for temperature, R is a gas constant. It doesn't change. And actually, when we're saying number of molecules here, it's actually number of moles. Some of y'all may remember from your days in science, moles is a way to measure how many molecules you have. There's this number called Avogadro's number. Y'all remember that? There are 6.02 times 10 to the 23rd molecules in a mole. It's just a way to measure how much of a certain substance you have. This is the ideal gas law. PV equals nRT. What does it mean? It's exactly what we've been talking about. If you draw your scuba tank, if you add air to it, you're going to increase the pressure. That's what this law says. Remember, when you have an equation like this equal sign is critical. And what it means is, if you increase something on this side, in order to keep it equal, you have to increase something on this side. So in the example of our scuba tank, if we add air in, we're increasing the number of molecules. Now in a scuba tank, the volume does not change, right? The walls are rigid. Scuba tank is a rigid container. The walls don't change shape. So in a scuba tank, the volume of the container has to stay the same. So that is a constant. So if you add molecules, you add air into the scuba tank, it's going to increase the pressure. That's what this law tells us. The ideal gas law tells us you add molecules, the pressure has to go up. And that's what your gauge on your scuba tank will show you too. Then you go scuba diving, you breathe air out, you take molecules out, your pressure drops in your tank. Also, if you take a scuba tank with air in it and you heat it up, increase the temperature, that's also going to increase the pressure. Now that's what happens in a rigid container. If you look at a flexible container, like a balloon, you know, when you blow up a balloon, it gets bigger and bigger and bigger. If you let air out, it gets smaller and smaller. The volume of a flexible container can change. So how does the ideal gas law work with a flexible container like a balloon? Well, with a balloon, since your volume can change, you've got to take that into consideration if you're changing things over here. If you start with a flat balloon that doesn't have air in it, that's got basically no air in it, right? But if you start to blow it up, so the volume is very small. If you blow it up, the volume of the balloon changes. The way you look at that with ideal gas law, until you get to a certain point, the pressure is not going to change a whole lot. At some point, the pressure will change, and you can even burst it. But with a flexible container, the volume usually changes more than the pressure. So if you say the pressure is not going to change much, but the volume can change, if you add molecules to a balloon, you blow up a balloon, you're adding molecules of air, and the volume increases. So this is going up, that goes up. Same way, if you have a balloon that has air in it and you heat it up, you increase the temperature, then you're also going to increase the volume. So that's basically the ideal gas law. It's a relationship between the pressure. This is of a gas that's contained in a container. It's how the pressure and volume are related to the number of molecules and the temperature. And what you need to be sure you understand, you need to know this equation, know what the letters represent, and you need to be able to answer the question, in a rigid container, if you increase the temperature, what does that do to the pressure? Understand what the relationships are for both a rigid container and a flexible container. And the key differences is, in a rigid container, the volume does not change. In a flexible container, the volume does change. Okay? And if you get confused on rigid and flexible, a rigid is like a scuba tank, the flexible is like a balloon. So, learn that equation, learn what each letter means, and make sure you understand, for rigid and flexible, the relationships. If you change temperature, is it going to change pressure or volume? If you change the number of moles, what's it going to change? Okay?